Heisenberg's uncertainty principle, a cornerstone of quantum mechanics. When you think of science, precision and certainty often come to mind. Yet in the world of quantum mechanics, there is a fundamental limit to how precisely we can measure certain properties of particles. This principle, discovered by Werner Heisenberg in 1927, is known as the uncertainty principle. Today, we'll explore what this principle means, how it works, why it's important, and how it has revolutionized our understanding of the quantum world. What is the uncertainty principle? At its core, Heisenberg's uncertainty principle states that there is a limit to how accurately we can simultaneously know certain pairs of properties of a quantum particle. The most well-known pair is position and momentum. If you try to measure the exact position of a particle, you lose precise knowledge of its momentum, and vice versa. This relationship is mathematically expressed as: where is the uncertainty in position, is the uncertainty in momentum, is the reduced Planck's constant approximately joule seconds. This equation tells us that the product of the uncertainties in position and momentum must be greater than or equal to a very small constant. In essence, the more precisely you know one property, the less precisely you can know the other. This principle isn't due to any technological limitations. It is a fundamental property of nature itself. The origins of the uncertainty principle. Werner Heisenberg developed this principle as he attempted to understand the behavior of particles at the quantum scale. He realized that the act of measurement inherently disturbs the system being measured. For instance, to determine the position of an electron, you might use a photon to illuminate it. However, the photon transfers energy to the electron, altering its momentum. This disturbance is not a flaw of the measuring instrument, but an unavoidable feature of quantum interactions. Heisenberg's discovery challenged the deterministic view of classical physics, where one could, in theory, predict the behavior of any system if all initial conditions were known. In the quantum realm, uncertainty is baked into the very fabric of reality, the double-slit experiment and uncertainty. The uncertainty principle is not just a theoretical idea. It has been observed in experiments. One famous example is the double-slit experiment. When particles like electrons pass through two narrow slits, they create an interference pattern on a screen, demonstrating wave-like behavior. But if we attempt to observe which slit an electron goes through, the interference pattern disappears, and the electron behaves like a particle. This experiment reveals the dual nature of particles and the role of observation. The very act of measuring which slit the electron passes through introduces uncertainty into its momentum, altering the outcome. This interplay between measurement and uncertainty lies at the heart of quantum mechanics. Why does this happen? The uncertainty principle arises from the wave-like nature of particles in quantum mechanics. When you measure a particle's position, you confine its wave function to a small region in space. This confinement increases the uncertainty in its momentum. Conversely, if you measure momentum with high precision, the wave function spreads out, increasing the uncertainty in position. This behavior can be visualized using the Fourier transform, a mathematical tool that relates the wave function's spread in position space to its spread in momentum space. Narrowing the wave function in one domain inherently broadens it in the other. This relationship underscores the fundamental interconnectedness of position and momentum in quantum systems. Applications of the uncertainty principle. Heisenberg's uncertainty principle is not just an abstract concept. It has profound practical implications in physics and technology. Here are some key applications. Quantum tunneling. Quantum tunneling occurs when particles pass through barriers that would be insurmountable in classical physics. This phenomenon, enabled by the uncertainty principle, is essential in processes like nuclear fusion in stars and the operation of modern electronics, such as tunnel diodes and flash memory. Electron microscopy. The wave-particle duality of electrons and the uncertainty principle set limits on the resolution of electron microscopes. Despite these limitations, electron microscopy allows scientists to observe structures at the atomic level, providing insights into materials, biology, and nanotechnology. Stability of atoms. The uncertainty principle explains why electrons do not collapse into the nucleus of an atom. If their position were too well defined, their momentum would be highly uncertain, resulting in a quantum motion that stabilizes the atom. This principle is crucial for understanding atomic and molecular structures. Quantum cryptography, the uncertainty principle, is a cornerstone of quantum encryption. It ensures that any attempt to measure or intercept quantum keys disturbs them, making eavesdropping detectable. This has significant implications for secure communication and information technology. Zero-point energy. Even in its lowest energy state, a quantum system retains some energy due to the uncertainty principle. This zero-point energy is observable in phenomena such as the Casimir effect and is fundamental to understanding the behavior of quantum fields. Philosophical implications. The uncertainty principle challenges our classical intuition about the universe. In classical physics, it was assumed that the universe operated like a giant clock, where the future could be precisely predicted if all initial conditions were known. Quantum mechanics, however, introduces inherent unpredictability. This unpredictability has profound philosophical implications. It suggests that reality is probabilistic at its core, leading to debates about the nature of determinism, free will, and causality. It also highlights the role of the observer in shaping reality. In the quantum world, measurement is not passive. It actively influences the state of the system being observed. The broader impact on science. Heisenberg's uncertainty principle has inspired new ways of thinking across disciplines. In quantum field theory, particles are understood as excitations of underlying fields, blending wave and particle descriptions. This framework has led to the development of the standard model of particle physics, which unifies our understanding of fundamental forces and particles. The principle also bridges the gap between quantum and classical physics. As systems grow larger and more complex, quantum uncertainties average out, giving rise to the deterministic behavior we observe in the macroscopic world. This transition from quantum to classical remains an active area of research, with implications for understanding phenomena like decoherence and the measurement problem. Conclusion. Heisenberg's uncertainty principle is a cornerstone of quantum mechanics, reshaping our understanding of reality at the smallest scales. It reveals the inherent limitations of precision and challenges our classical intuition about how the universe works. Despite these uncertainties, the principle has enabled groundbreaking advancements in technology and science, from quantum computing to secure communication. As we continue to explore the quantum realm, the uncertainty principle serves as a reminder of the mysterious and interconnected nature of the universe. If you've enjoyed exploring this fascinating topic, don't forget to like, comment, and subscribe to our channel. Together, let's unravel the mysteries of the quantum universe.